Okay, wonderful. So our second speaker for today is Mario Vasa, and he's from the Institute of Organic Chemistry, and I think we're going to get a basic math lesson today as well. Please go ahead.
Okay, yeah, so thank you very much. Actually what I want to show you today is a bit of an introduction to some research going on in our group where we center on asymmetric catalysis using synergistic catalysis, synergistic catalyst modes. And what I want to show you today is really, that's the main task, major goal of this talk, to show you what these three terms mean. But before I really go into any details here, let me briefly convince you why chemistry and especially synthesis is of value. You all know that the pharmaceutical industry is one of the biggest industries on this planet in terms of revenue and sales. And when you look at the drugs that we have available, of course, the drugs are pretty diverse in their structure as well as their origin. So on the one hand side, we have the big biological products where we also have all these commonly used, very, very prominent vaccines. On the other hand, we also have this part of the pharmaceutical market, which is called the small molecule drugs. Small molecule drugs are really consisting of small molecular entities that are usually made from scratch by classical organic synthesis. And also these drugs are maybe not as prominent as something like these AstraZeneca or these Pfizer COVID vaccines. They are really big in their sales. So what you, for example, see here, Eliquis, it's a drug for cardiovascular diseases. It's the 5th best-selling drug on the market globally, and it had last year's global sales of roughly $17 billion. So you see it's a really big market. And this is the market which is especially interested for organic synthesis because somehow you have to make these molecules. And a lot of the research going on in organic synthesis currently really centers around the development of methods to really access these molecular entities. And it's an ongoing goal, so organic synthesis has been prominent for the last 140, 50 years making drugs, and it's getting more and more complicated. And one thing that you commonly use in organic synthesis is that you somehow rely on catalysis. So what does catalysis mean? In the end of the day, if you imagine that you have certain chemical transformation, then very often chemical transformations are hindered. So if you just would wait for nature to carry it out, you'll wait forever. And at a certain point, this is really good for our survival because otherwise we would all burn to carbon dioxide and water immediately. So it's good that we have this kinetic hindrance of a chemical transformation. But of course, as chemists, we want to speed up chemical transformations. And what we often do is we use a catalyst. And this catalyst can have multiple ways of interacting in the reaction, interfering with the reaction. But in the end, what it does is it breaks down the reaction. So it makes a reaction which is pretty hindered, which is illustrated by this hill here. And it breaks it down in single steps, which are much more likely, much more easily possible. And the interaction of the catalyst with the reagents is pretty complicated depending on the system, but in the end of the day, what this can do, it can allow you for transformations that are otherwise only hardly possible. And over the years, the development of catalysts has really been very, very prominently also honored by looking at the Nobel Prizes that have been given to catalysis-related research. There have been Nobel Prizes for catalysis-related research using enzymes as catalysts. There have been Nobel Prizes for transition metal catalysis. And what is especially interesting for our group is the use of organic molecules for catalysis. So this was also really popularly honored by the Nobel Prize in 2021, going to these two gentlemen, Ben List from Germany and Dave McMillan, native of Scotland, now working in the US, who were pioneers in the field of asymmetric organocatalysis, so the use of small organic molecules for catalysis. Now, why is this interesting? When you look at an organic molecule is not flat. So the most simple organic molecule that we have is methane, and methane already is a tetrahedron. So what we always have to do is when we look in organic synthesis, we somehow have to make sure that we address the three-dimensional structure of a molecule. It's getting even more complicated when we look at molecules where we have a carbon which has 4 different substituents. Because if we have a carbon with 4 different substituents, at the end of the day, we have 2 options how this molecule can be arranged, or 2 options how these 4 different substituents can be arranged. It can be either arranged like this or like that. So what I indicate is this bold arrow shows you it goes out of the plane towards you. This dashed arrow shows it goes to the back. So you have actually a tetrahedron with 4 different corners. And if you look at these 2 possible orientations, we call these 2 molecules, image and mirror image, or with respect to organic nomenclature, we call it enantiomers. So these 2 molecules that you have here, depending on the different orientation of the substituents, look like image and mirror image, or if you look at a body, it looks like right hand and left hand. So in the end, they have the same constitution, they have the same groups, but they have a different orientation in space. And this phenomenon that you have 2 molecules that behave like image and mirror image is called chirality. So it's a long-known term. This term does not only relate to chemistry, it relates to other aspects in life. But what is important for you is that these 2 molecules, image and mirror image, which we chemists call enantiomers, have different chemical properties, or can have different chemical properties. So I've shown you 2 examples here. On the one hand side, we have limonen. Limonen has here this so-called stereogenic center. That's the carbon with 4 different substituents. There are 2 arrangements in space, the image, the mirror image. This one here, this orientation space, gives you the classical lemon type flavor. This one gives you an orange type flavor. So in this case, it's just a different flavor. But of course, it can be even more dramatic when it comes to pharmaceuticals. And what you see here is thalidomide. Thalidomide was a drug brought to the market in the 1950s, 60s against morning sickness of pregnant women. And it was sold under the name Contagan. And some of you are familiar with this scandal because the problem was that this image here, this enantiomer, had the known or the wanted sedative properties, whereas the other enantiomer had these unwanted teratogenous properties. And since this moment, it has been really known that when you make a drug, when you bring a drug on the market that is chiral, where you have a stereogenic center, you really need to address the stereogenic center. You need to be able to control it. And the way how catalysis can help you in this way is that you can use an achiral starting material, so a starting material which has no image-mirror image behavior, and somehow the catalyst helps you to favor only one enantiomer. So how can we simplify this? It can be best simplified, in my opinion, when you look on a triangle with 3 different corners. If you look at such a triangle, it's flat. We can look at it from the front or from the back, from the top or from the bottom. If you now attach another ball to this triangle, you can either attach this ball from the top or from the bottom, and what you will get is you will get 2 times a tetrahedron. If the ball comes from the top, you get this tetrahedron with this orientation of the 4 substituents. If the ball comes from the bottom, you get this one. And again, if you look at these 2 tetrahedrons, you see that they are image and mirror image. And usually, if you take any random triangle and you do this, you have a 50-50 chance that the ball comes from the top or from the bottom. What we now want from our catalyst is we somehow want the catalyst to block one of the 2 phases. That's the major job of a chiral catalyst. You do a transformation and you make sure that you form a tetrahedron phase selectively only from one side. Now this can be done by a lot of different catalysts, and in my group we are very much interested in organocatalysis. So we want to use small organic molecules, so no metals, no big enzymes, to control such reactions. And one program that we have in my group is that we look on catalysts which have a quaternary ammonium group as the catalytically active side. We use these catalysts then to develop new methods. So we want to develop methodologies using such building blocks here to make new molecular entities of a given complexity. And we also want to use this methodology to make molecules of maybe biological interest, like amino acids, alpha amino acids, beta amino acids. We made this molecule, which also has some drug-like properties. So everything in my group centers around catalysis, designing catalysts, and applying them to make new molecules or to make molecules with given properties. What, however, makes it sometimes a bit complex is that we really have to choose the right group that does the catalytic job, so the right working horse. And sometimes we not only stick to one catalyst, but we also want to stick to two distinct catalysts or two distinct catalytic motifs. Imagine you have one catalyst motif that has a certain reactivity, selectivity, whatever. You have a second catalyst which can do something else. What you can do is you can think about using the two in a combined synergistic use. If we do this, and if we design it well, and if we're lucky, we can have improved new, maybe even new reactivity that a normal catalyst cannot do. We can have improved selectivity, and maybe we can molecules that we could not make before. So this is the major goal, what you want to do in synergistic catalysis. And of course, you can also think about applying it to asymmetric catalysis so that you combine all this. Now, when we do synergistic catalysis, you have in the end two ways how you can combine these two catalyst motifs. The most easy thing is you use both of them independently, you throw it in your flask and you hope that they work somehow together. Sometimes this works brilliantly, and if this is working, fine. The other option is you combine two catalyst motifs in one new catalyst, which you call now a multifunctional catalyst, and apply this one. And we have been working on both of these for years, and I just want to show you one example here. This has been something which has been going on in my group for 8 years now. We had designed a catalyst where we have an ammonium group. This is our one working horse. We have here another working horse, so it's a different functional groups. So both of them are connected in one catalyst motif, and then you can do a lot of different transformations here. This is more for the chemists in the audience. So you can install heteroatoms, you can make molecules where you have more complex scenarios, you can make carbon dioxide insertion. So this is really carbon dioxide fixation chemistry. So this would go really beyond the scope of this lecture to go more into details here, but if you're interested in this, please let me know, we can discuss this afterwards. But the take-home message is that all these reactions here have only been possible in our hands when we use a catalyst where we really have two distinct catalyst motifs. So really a synergistic use of two different catalyst motifs. Good. That's all I wanted to show you. So I hope you have a bit of an impression what we mean when we talk about synergistic catalysis, especially in the asymmetric realm. And I want to close with starting with thanking my group. So these are all the co-workers that have been involved in our research over the last 10 to 12 years. And I also want to thank my collaborators and especially the funding agencies. Most of the research came from the FWF, but especially the Synergistic Catalysis project was over the last 2 years very nicely funded by the LIT. So a big thank you for that one. So we could do something here which was not funded actually by the FWF. We could do it now with the LIT funding. And with this, I want to stop and thank you for your attention.